All right, guys. So let's do a couple more examples, and I have another example here with monatomic, diatomic gases. You have a question there where they ask you, you have a cylinder. So you have an ideal gas, basically, where you have the number of moles equals to 11.2. You have the initial temperature as 22.4 Celsius, so we have to change that to Kelvins, and a volume of, so in meter cube, 0.310 meter cube. So there's a whole bunch of questions there, right? What's the pressure in pascals and all that? So PV equals to nRT. Now that will be the initial pressure. Right, so you have it there. P initial, volume initial equals to nR, initial temperature. The pressure times the volume, which is in meter cubes, that's fine, equals to 11.2 times 8.31 nR, and temperature is 22.4 plus 273. So 295.4. So let's see, everything is in the right units. So we multiply the right-hand side. And then we divide by. So it's a large value of pressure. I get here 88,688.61. 88,688.61. That's in Pascal. That's why if you were to write this in atmosphere, you will divide that by 100,000, right? So if I were to divide this number by 100,000, just so you know, it will be 0.88, 0.89 atmospheres, okay? So that's why we use atmospheres a lot, especially in chemistry, right? But here it is. So that's the pressure. That's just one of the questions. The second question is asking you to find the internal energy of the gas. Now, this is for neon. It can be argon, it can be any of the noble gases. And those gases are monoatomic. So if you want to find the internal energy for a monoatomic gas, the initial internal energy, right? UI, that will be 3/2 of nRT. And the reason that's the equation is because we are using CV equals to 3/2 R. The pressure is changing, as we're going to see, and the volume stays the same. That's in the question. So that's why we use CV. If the pressure was constant, we use CP, 5/2 R. And that's something that we're going to use in another question I have here. Okay, so that's important. So if I want to find the value of this in joules, 3/2 of 11.2 times 8.31 times the initial temperature, 295. Everything is in the right units, so you will get it in joules, just like we did with the pressure. $41,240.2. Joules. Okay. Suppose the gas expands at constant pressure. So now you are assuming it's going at constant pressure to a volume of 1 meter cube. How much work is done on that? So now they're changing the value, right? So here we have, what is my window here? So suppose the gas expands at constant pressure to a volume of 1 meter cube. How much work is done on the gas? So you want to find you want to basically use the equation, the first law of thermodynamics, right? Now, it says a constant pressure, sorry. So you can just use P delta V. Okay, so the pressure that we found, right? We found the pressure, you just use P delta V. Okay. So I want to leave this in one, not that we can erase this. Let's just find the value, right? The values that we found. So we need this value. It's a constant pressure, 88,688.61 Pascal. Volume initial is 0.310 meter cube. Volume final is 1.000 meter cube. Right to 1, yeah. So the work is just P delta V. That's for an isobaric process. So you just use the pressure times this minus that. So let's just put here 1. This is just for sig figs, by the way, guys. So, right? So 1 minus 0.310 times 88,688.61. So that's 61,195. So that will be 61,195.1 joules. Now, let's read the question. It says, how much work is on the gas? That's work on the gas. They like to trick you guys a lot with this. If you put a positive, it will mark 1. What's the temperature of the gas at the new volume? So we need to find the temperature of the gas at the new volume. So we need PV equals to nRT. So yeah, we have the new volume. We have the pressure, which is constant. We have the number of moles. So we can find the temperature, right? So you you will just do P final, or P is constant, P final equals to NR T final. The temperature will be PV final over NR. P is all that, V is this, N is, let me take a look at the problem. 10 points up, sorry. 11.2, so 88,688.61 multiplied by 1 divided by 11.2 and R 8.31. Let me see if you guys can see that. Okay, so let's take a look. So it will be in kelvins because we have all the right units. $953. $953 kelvins. And why are they asking you for that? Because now they want you to find the internal energy of the gas when the volume is 1 meter cube, right? So we can use free half of nRT. All right. So let's erase this. You have the pressure value there, okay. It's a monatomic gas, don't forget. So the U final, right? Which will be 3 halves of nRT final. 3 halves. That. And they ask you for that because they're going to ask you for the change of internal energy. So you're basically doing this step by step. $133,046.4 joules. That is the U final. So now you can compute that change of internal energy. Now I erase that. So please, you know something. Let's recalculate your initial. That was 3 halves of N R. And the temperature is so let's see, what was this again? Yeah, 41,240. 0.2. So the change of internal energy, delta U, that's U final minus U initial. So you have the values there. $91,806.2 joules. Why they ask you that? Because now they ask you for the heat. Q equals to work plus delta U. But the work was negative, right? The work was $61,195. Negative. So negative 61,195.1 plus 91,806. It was negative because the work was not on the gas. $30,611. Yeah, joules. That's basically the heat on the system. Okay, so nice problem where you have a lot of variables. Okay. That's one of the last problems. No, not like that's problem 5, problem 6. Okay, let's show you a problem I have here. It's a bit different. Let's go back to a PV diagram sort of problem. You see, we haven't used much of Boyle's law. I mean, we have in some way or form. But there are problems that you can find in the book as well, when they give you the formula. So you may be giving a PV diagram like this, or a diagram, not a PV diagram, any diagram, because you can plot volume in meters cubed as a function of temperature in kelvins. And they give you an initial state, 180 kelvins, and then 2 meter cube, 360. This is stage B, stage A, and the gas is going from A to B. Like that. And you are being given that during that process, the gas absorbs. So Q absorb is equal to 5 calories. With that. Find the change in internal energy in joules between A and B. So if it was a PV diagram, you can find the area under the curve, and then that's work, and then Q minus W, that will give you delta U. But in this question, it's a volume versus temperature. So be careful, right? So how will you do that? You have to use the equation for U. But there are 2 equations you can use. 3 half of nRT or 5 half of nRT. How do you use each one, right? It depends on the type of process. If you have a constant pressure, you have to use Cp. For a constant volume, you use Cv. So for a state A, pressure at A times volume divided by the temperature at A is that. Let's compare this to pressure at B, volume. So this is what happens though. Pressure at B is equal to pressure at A is equal to pressure at B. This is Boyle's-Charles law. That's like ideal gas law. Moles are constant. The R is a constant, right? So this is an isobaric process. You see, you can discover these things. They don't have to tell you. If it's an isobaric process, then we find the we can find the value of delta U. You see, the heat for this type of process is 5 calories. That's 5 times 4.18. That is 20.9 or 21 joules. So 21 is equal to 5 half of nRT. Why? Because my Q is equal to NCP delta T, because it's an isobaric process. My delta U, like I've been doing in the problems from web assigned, yep, my delta U is NCV delta T. That doesn't change. That's what we've been using that equation for the previous problem, right? 3 halves of nRT. So 3 halves of nRT. But wait a second now. 5 halves of nRT is 21. So nRT is 42 over 5. 42 over 5, 8.4. That goes here. 3 halves of 8.4. So now 3 times 8.4 divided by 2, I get 12.6, 12.6 joules. That's the change on internal energy. So in the previous problem, we didn't use this. 5 half or 3 half. The heat, the equation for heat depends on the type of process. If it's an isobaric, NCP delta T. If it's isochoric, NCV delta T. Okay? Let's, I just wanted to show you this as well, and let's see if we can do another question from here. An ideal gas is compressed from this volume to this volume while in thermal contact with a heat reservoir at T. Okay. During the compression, the piston moves down a distance. Okay, they give you that so you can find. Yeah, they give you the force so you can find the work. Find the work done on the gas. That should be force times distance. Find the change in internal energy. Yeah. And find the thermal energy exchange between the gas and the reservoir. Okay. So the temperature is always at 295. All right. So let's draw this. Or let's actually show you what variables you need. You are pushing down a piston like I show you there. You don't need the area because you already have the force. So you're going to do work on the gas. So the work is going to be negative. .12. The force is 45.5 kilonewtons. Be careful with that. Okay. So let's start with the work. Right? That's the figure. Right? So then we are going to find the amount of work done on the gas. The work done on the gas is just force times distance, negative force times distance. Negative 5,460 joules. It's work done on the gas. Directly, guys. Delta U is equal to 0 joules. Why? Because the temperature in that problem is constant. So this is an isothermal process. And the internal energy, the change on internal energy always depends on the delta T. So if you don't have change on temperature, you don't have. So then part C, find the thermal energy exchange. Then you just use the first law of thermodynamics. Q equals to delta U plus W. Delta U is 0. Q is negative. Here you are. That's your Q, that's your delta U, and that's your work. There. For that problem. All right. What else we have here? I think that covers everything in this assignment and in thermodynamics. If you have more questions about this, please let me know. I might eventually do more examples with PV diagrams, but I did a couple already, and I think that should be more than clear. Okay. I'll see you guys on the next video. Have a nice day.